to try this warm-up and then play the video to check your answers. So let me go over the answers here. So the first one was find f of g of 2, which means substitute -2 into the g function everywhere there's an x, and simplify that so I get -2 when I've done that. And then -2 is input into the f function, which means 2 times -2 minus 1, which simplifies to -5. So f of g of -2 is equal to -5. The second one is asking for g of f of x, which means we're putting the f function into the g function everywhere there's an x. So the entire f function is replacing x in the g function. So instead of x, I have the quantity 2x plus 2x minus 1 squared. Instead of x, I have, again, the quantity 2x minus 1, and that's times 3 because the equation says so. So then I properly square the binomial using either generic rectangle or FOIL, if that's how you learned it, and that gets us 4x squared minus 4x plus 1. Then distribute the 3, and we get 6x minus 3. And then lastly, combining like terms, and that gives us our final answer, g of f of x is equal to 4x squared plus 2x minus 2. Okay, so that was the warm-up. Next, so we talked about in class how to graph y equals x. Now that should be review for you. You learned how to graph y equals x in Algebra 1. So we started with just a table. And I just input some negatives and 0 and positives. And we know that if y equals x, then all the x values are the same as the y. So -2, -1, 0, 1, 2 are the y values as well. So if I were to plot those points on a coordinate plane, I would just have 1, 1, 2, 2, 3, 3, so forth, -1, -1, -2, -2, 0, 0. So if I connect those, I get the line y equals x. Okay, so then after that, the next thing we did was we talked about how we could adjust those points to move the graph 1 unit to the right. So if we are moving the graph 1 unit to the right, right 1, then we're going to adjust the table. So we talked about in class, if the graph's moving 1 to the right, then the x is going to be affected because x is left or right. The y's are going to stay the same. So I'm just going to copy the -2, -1, 0, 1, 2 that we previously had. So then I'm going to adjust the x values to move them 1 to the right. Well, 1 to the right means the x value would increase by 1. So I'm going to add -2 plus 1, and that gives me -1. -1 plus 1 gives me 0. 0 plus 1 gives me 1. 1 plus 1 gives me 2, and 2 plus 1 gives me 3. So now I have those coordinate points that I can plot on just the same coordinate plane is fine. So -1, -2 is right there. 0, -1 is right there. 1, 0 is here. And 2, 1 is there. And 3, 2 is there. And if I connect, I'm getting a line that is shifted 1 over to the right from the original line. Okay, remember our original, we're always referring back to y equals x. Okay, so then the next thing we did was we talked about what the equation would be for each of these lines. So we know y equals x is the original. The one that shifted over to the right 1 unit, if I check the slope and the y-intercept, I'm seeing -1 is the y-intercept and 1 is the slope, which means the equation is y equals x minus 1. Okay. The next thing that we did was, again, referring back to y equals x, the original graph, we adjust the points on the table to move the graph 1 unit down. Okay, so let me make myself another table here. So if I'm, again, referring back to this original table, y equals x's table, and if I'm moving the graph 1 unit down, well, 1 unit down means the y values are going to be affected. The x values are going to stay what they were. So -2, -1, 0. Let me just scroll down a little bit here. 1, 2. And if the y values are moving down 1, down 1 is going to happen from subtracting 1. So I'm referring back to my original y values, and I'm subtracting 1 from each. So -2 minus 1 is -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. And 2 minus 1 is 1. So that's giving me those values. So the next thing we did was we added those points, we plotted those points on the graph. Well, look what happens if I start plotting these. -2, -3, it's right about there. -1, -2, it's there. 0, -1 is there. All these points here are already on that graph that we just did of y equals x minus 1, which means that the equation for y equals x shifted 1 to the right and the equation for y equals x shifted 1 down are both y equals x minus 1, which means that a shift right is the same thing as a shift down. Okay, and this is only for linear. This is only for y equals x equations. Okay, so then what we talked about next was the fact that if right and down are the same, then left and up are the same. Okay, and we also talked about because right and down are the same and the equation is y equals x minus however many units, in that case 1. Then left and up are the same, which means the equation would be y equals x plus whatever, however many units the graph is being shifted up or left. Okay. All right. So this is just talking about what we just did. We compared with each other and we discovered that for linear, for y equals x, if we add a number, we'll just call that h, however many units that is, onto the end of x, that is a shift up or left h units, however many units that is. And if we have y equals x minus h, that is a shift down or right, again, h units, whatever h represents, whatever number. Okay. Next. So what we just talked about, shifting left, right, up, down, those are called translations. That's the term there. Or we sometimes hear, translate this graph 4 units to the right. Translate's just another word for shift. Another term we looked at is called transformations. Transformations is when the graph gets stretched vertically or compressed vertically. So let's look at that. So again, if I'm referring back to my original graph, y equals x, so 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so forth, -1, -1, so forth. So there's my original graph. if I put a number in front of the x, so right now we know y equals x, the number in front of x is just 1. But if I were to, let's say, look at y equals 2x, okay, well 2x, we know from our experience with lines in Algebra 1 that 2 is just the slope. So what happens if we put the 2 as the slope, what happens to the line is that it'll become more steep. Okay, so it'll still have 0, 0, but it'll be steeper. Okay, and another term for that is a vertical stretch. If you picture, if you're holding on to the ends here of the original graph, and you pull each end and pull it vertically, so up and down vertically, you would stretch that graph vertically and you would get the new graph y equals 2x, okay, which would have a steeper slope. So a vertical stretch comes from the slope being a number that's larger than 1 or a number whose absolute value is larger than 1. So if it was negative, we'd be talking about a negative slope line, but it still could be vertically stretched or vertically compressed. So if I just put an a in the front, we'll just call that number in the front the slope a, it'll be a vertical stretch if the absolute value of a is greater than 1. For example, y equals 2x. 2, the absolute value of that's 2, and 2 is greater than 1. Y equals negative 2x. Well, the absolute value of negative 2 is 2, and 2 is larger than 1, so y equals negative 2x has been vertically stretched as well. On the other hand, a vertical compression comes when the absolute value of a is less than 1. Again, absolute value, because it could be positive or negative, but the value itself of the slope, not looking at the sign, the value itself of the slope, if it's less than 1, like y equals 1/4 x, let's say, that has a slope of 1/4, that graph would be vertically compressed. And what does that mean? Coming back here, vertically compressed, again, I'm going to go back to the original y equals x, and I'm going to put my hands on both sides, one above and one below the arrows, and I'm pressing down vertically. So pressing down, what would happen? Well, we'd have a line still going through 0, 0, but now this line has been vertically compressed, which means it's less vertical, less steep, more narrow. That would be y equals 1/4 x. Okay, so those are transformations: vertically stretching, vertically compressing. Okay, the next thing we did was we took a look in class at the graph y equals the absolute value of x. So if you forget what that looks like, let's do a table. -2, -1, 0, 1, 2. So the absolute value, remember, that's the distance away from 0 on the number line. So we know that negative numbers become positive because when we're talking about distance, distance is always positive. And positive numbers stay positive. So -2, the absolute value is 2. -1, the absolute value is 1. 0 stays 0. 1 stays 1. And 2 stays 2. So if I draw myself a coordinate plane, which you should put into your notes, and plot some of these points, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, we're remembering, hopefully, that the absolute value of x, y equals the absolute value of x, is a V shape with its vertex located at 0, 0. Okay, so we're going to take a look at the translations or the shifts for the absolute value graph. Notice as we go over this, they are similar to linear, but just slightly different, because with linear, a moment ago, we said that a right shift was the same thing as a downshift, and a left shift was the same as an upshift. Well, with absolute value, they are 4 separate shifts. It's not that 2 of them are going to be the same. But what is similar is that if we're talking about, if we have a minus sign, that's going to be either a right shift or a downshift. And if we have a plus sign involved, that's going to be either a left shift or an upshift. So now we need to talk about, excuse me, which one's going to be which. So we can take a look at these. These are just a few examples of different places that we could, in this case, add 2 or 1/2, or subtract 2 or 1/2, or multiply by putting a number in the front. Okay, so we'll start with the vertical stretch and the vertical compression because they are identical to linear equations. Okay, it's still the same in terms of the fractions that are less than 1 or greater, or non-fractions that are greater than 1. Still going to be a vertical stretch or a vertical compression. The only difference is instead of being in front of x, now the numbers are going to be in front of the absolute value of x. So we know that 5 and 6 here, if these are my examples, numbers 5 and 6 are going to represent a vertical stretch and a vertical compression. So it's our job to figure out which one's which. And as I said a moment ago, the rules are the same as they are for linear. So that means that the one that has a 2, that's going to be a vertical stretch because the absolute value of 2 is 2, which is greater than 1. So this is a vertical stretch. On the other hand, 1/2 for the a value, the number in the front, is going to be a vertical compression. Okay. So now we just need to talk about the other 4. And think about what I said a moment ago. Subtracting is going to be either right or down. Adding is going to be either left or up, just like linear. But the difference here is we have subtracting inside the absolute value and we have subtracting outside of the absolute value. We have adding inside the absolute value and we have adding outside of the absolute value. So you could play around with this if you had more time and graph each one of these by making a table. We're not going to take the time to do that, but I will tell you that when you are subtracting inside the absolute value, that is a right shift. Right shift. Okay, again, similar to linear, when we were subtracting 2, that was a right shift or down. So this is translating right 2. Okay, so if -2 inside the absolute value is right 2, then the opposite of that would be adding 2 inside the absolute value, which is going to be left 2. So left and right are the numbers that are inside the absolute value, which leaves us with up or down on the outside of the absolute value. And now that should make sense to you. So obviously adding is going to be up, just like linear was. And subtracting is going to be down, just like linear was. Okay, so if I were to summarize this, we usually use this equation. It's a general equation for absolute values. So make sure to write that in your notes. This is the equation for an absolute value where hk is the vertex. Think about that a moment. We said that the vertex of this basic absolute value graph was at 0, 0. So if I shift that absolute value graph, which has a vertex at 0, 0, if I shift it, -h means right h units. So if I shift it from 0 to the right h, that takes me to h. And then plus k means up k units. So if I shift it from 0 on the y-axis up k units, that's going to take me to k. So the vertex shifted or translated from 0, 0 to hk. So now the vertex is at hk. Okay? And as we said a moment ago, h is going to be your shift left or right. In this case, the way it's written here, -h would be right h units. And if it said x plus h, that would be left h units. And k on the end is our up or down. In this case, because it says plus, that's up k units. And if it said minus k, that would be down k units. A is the exact same as it was with linear. If the absolute value of A is less than 1, that's a vertical stretch. And if the absolute value of A is greater than 1, whoops, I have that backwards. Strike that. Less than 1 is the vertical compression. I said those in the opposite order in the last example. And greater than 1 is the vertical stretch. Greater than 1 is the vertical stretch, so like 2, 3, 4, so forth. Less than 1, like A is 1/2, 1/3, 1/4, or remember negatives are fine too. So if A was -2, that would be a vertical stretch. If A was -1/2, that would be a vertical compression. Okay, so how do we use all this information? Well, our ultimate goal is to look at the equation of an absolute value and to be able to graph it without using a calculator. So let's think about this a moment. Remember, we had A times the absolute value of x minus h plus k. So A in this case, there's no number there, so we know that's just a 1, so it has not been vertically stretched or compressed. On the other hand, we see plus 3, so let's think about what shift that would be. So plus 3, we know, is a left 3. So I'll write that. And then I'm thinking about what's on the end here. We have after the absolute value -1. Well, -1 is down 1. So remember, our vertex starts with the most basic one, with y equals the absolute value of x. The vertex is at 0, 0. So if I'm starting at 0 for x and I'm going left 3, that takes me to -3. And you can look at the graph if you need to. Starting at 0, 0, left 1, 2, 3 takes me to -3. And if I'm starting at 0 on the y and I'm going down 1, so 0 and down 1, that takes me to -1. So the vertex is at -3, -1. So I'm going to do that. Starting at 0, 0, left 1, 2, 3, down 1 takes me right there to -3, -1 for the vertex. Now what I'll do is, if you remember back, or actually we'll just look back a moment, to our original graph, we had points also at 1, 1 and at -1, 1. So I'm going to go now to 1, 1. Now I'm not going to plot a point there, but I'm just going to hold my pencil there. So I'm starting at 1, 1, and I'm again going left 3 and down 1 from the point 1, 1. So left 1, 2, 3, and down 1. There's my point. And now I'm going to the other point at -1, 1 on the original graph, y equals the absolute value of x. And I'm going left 1, 2, 3, and down 1, and I'm putting the point there. 3 points determine an absolute value graph. Now I have 3, so I can certainly just sketch in my absolute value graph from there. And I'm just going to label the vertex. And that's how we graph y equals the absolute value of x plus 3 minus 1. Okay, so think of the shifts first. The shifts will help you come up with the vertex, plot the vertex, and then apply those same shifts or translations to the other 2 points, any other 2 points on the original absolute value graph. I just chose 1, 1, and -1, +1, and I just translated those points as well. So once you have 3 points, and again, we have 1 here, and the vertex, then you can plot your absolute value graph.